Good morning.
Morning, Doug.
Good morning.
Morning.
Thanks for dragging yourselves out of bed and improving yourselves. I love it. Let's see.
Can I ask you a quick question about the homework assignment?
I would love that.
There was 6.6. There was two assignments. There was a physical applications one and there was a surface area one. And the second one isn't assigned anymore.
Yes, that is a good question. So I went in there this morning and I noticed that that was mislabeled in the sense that the physical application chapter is 6.7 and they were both labeled 6.6 in there. 6 points. So I relabeled it 6.7 and then I decided that you guys have had like a quiz due yesterday and projects lately, kind of a lot going on. So let's not have a 6.7 assignment. So I went hide, gone. So
Okay. Thank you.
So what I want to do today is it's the coolest stuff by far, but I just don't want to, I want to just show it to you and just let you enjoy it and think about it and see what integrals can do today, but with no assignment. Frankly, another project brews here. In other words, I could, this is just super cool. I could spend 2 days on it. I could give you 3 projects. I mean, it's just really cool, but come on, man, give us a break. Let's let us pass calculus. I get that. So what I want to do instead is just kind of show you some of this stuff and give you some of the physics applications and and I've been alluding to this a little bit, the entire time in this class, just, what integrals really are. They're the ability to add lots of little things together. And I've, done little forays into what that means and so forth. So all I want to do today is just play with that and show you just some of my favorites. So this is sweet. This is awesome. Stoked to show it to you. So let's see. Justin, April, Thomas, thank you guys for showing up face to face. I appreciate that. I know it's early. Person doesn't want to get their hair all fixed up. Look at this hair, huh? So what? Veil. No fixing that, is there, Justin? No comb's gonna make any progress with that wig.
Yeah, not now that it's like slowly going back here. This gets more puffy.
Traveling south a little bit. I'm pretty sure you could fix that with a Sharpie. If you want some help, I'm in. So really good news, my friends. 6.7 applications. And I went into, as April just asked, but for those of you that are late, no assignment. Yes, no assignment. You've been doing a lot of stuff and we're getting ready for a test. So anyway, a whole bunch of applications I want to show you. Let's see. I don't know which one to start with. Let's start with DAM math. That's a good one. DAM math. So are you familiar with the term? I would imagine the answer to this is no. Hydrostatic pressure. It's really 3 words. What do you think that means? Hydrostatic pressure.
It means a pressure involved with water that's stable.
Yeah, static means not moving. So there's dynamic water, which is when someone squirts a hose at you, and if it happens to be a fire hose, you're probably going to get knocked over. But hydro is water, static is not moving, pressure. In other words, if you are at the bottom of a pool, for instance, there's a lot of weight on you. And again, there's a whole, I wish I could go into this. I could teach the whole class on this today, but the scuba diving is a part of this. In other words, you're way down there in the bottom, but we're not like a fish. We can't have water coming in and out of us to equalize the pressure. So when you're down there, you have to breathe pressurized air or you'll just go and smash. And you don't kind of notice that, but as a human being, like if we went down to that depth, you just smash. One time I hiked Mount Shasta and I took a Pepsi with me. And so I got to the top. Yeah, I made it. Pop the top open, drink my Pepsi. Woo! Close the lid, throw it back in my backpack, start hiking down. Got home, got my backpack out. What did I see with my Pepsi bottle, my plastic Pepsi bottle? What did I see when I got another backpack?
It was compressed.
It was utterly smashed because the air pressure at 12,000 feet is not very high. And what I did is cap that off. And so now I have that pressure inside there. And then I go back down, and that's just air. We're not even talking water. Air weighs not very much. Isn't it like 14 pounds per, what is that square? I forgot. Square foot? I forget. But air actually weighs something, but it just doesn't weigh as much as water. But by the time I got back down, I went from 12,000 feet back to Medford, which is like 1,500 feet. The pressure on the outside, there's so much air pressure on the outside that bottle didn't just like slightly crinkle. It was like gone. There was no air in it at all. I mean, it was the weirdest thing. I was like, wow. And that's what happened to you if you swam down really deep. And so in the end, you have a regulator on a scuba tank that increases the pressure of the air you breathe to balance it out. In other words, it's pushing back at the same pressure that the water is pushing in. And it actually adjusts as you go deeper, which is why that's called a regulator. It's regulating the pressure. So there's a ton of pressure down there. So another funny thing. So I'm a kid. I'm a kid of the 70s, and it's like, let's go swim. Let's go swimming. Well, you swim to the bottom of the pool, and that's really fun, except for you can only last like 30 seconds down there. And then you run out of air and you got to come back up. And so, you know, I got a brilliant idea. I'm going to swim down there with the garden hose. And then I'll just breathe and I can hang out down there. Except for that didn't work. It seems like it would work. Why didn't it work? I'm at the bottom of an 8-foot pool.
Because of the water pressure.
There is so much water pressure down there. Water weighs 8 pounds a gallon. There is so much water pressure 8 feet down that it's like having a stack of weights on your chest. I couldn't, my muscles would not inhale enough to even get air in there. So it's like I have my mouth on the hose and I couldn't even, like, it was the weirdest thing. It's like I couldn't suck. So then I had to swim to the top. I was like, dang it. So hydrostatic pressure is a thing. Now let's do some dam math. So I'm going to make this easy on you, but I could, again, spend the whole period with this if I wanted to, but let's make this really easy. So in any dam, they've got some kind of a door at the bottom that sort of lets water out. And they always let that out at the bottom of the dam, which is why downstream from Lost Creek Lake, if you've ever went rafting down there, even in the summertime, it's just freezing. And that's because it's coming out of the bottom of the lake. Well, they don't let it out of the top because then that would erode the top of the dam and destroy the whole thing. So there's like a door in there. There's some way to kind of open the door. Well, I want you to think about how much pressure is actually on that door. So this is our dam door down here. And let's see, I got to look up some conversions because I kind of forgot all these things. So let's say this door is a mirror. I don't know, 6 feet wide. And we'll say it is, I don't know, 8 feet tall. And it's rectangular. And so the idea is basically lift the door up a little bit, you know, attach a cable to the top of it and turn on some kind of a winch and just lift the door up a little bit, and then water kind of gets out the bottom. And if you lift it way up, then tons of water comes out. So you just kind of control that. So it's probably on some kind of a screw system, right? Where you can lower it, raise and lower it. Like a cable wouldn't work because you could pull it up, but then you wouldn't be able to push it back down. So some kind of a cable, and I'm just making this up. I haven't looked at what's going on there. But of course that door would be pushed against something metal that's sealed, and it would need to be able to roll a little bit. Like there's a ton of friction there and so forth. So you gotta like, how you're the engineer, you're the calculus nerd, like design that system so it'll actually work. Well, one of the things you got to understand is how much pressure is pushing that door against the seal. And think of it as just like a door in a house, and it closes against kind of a jam. Well, it's the same kind of a thing, I would assume, except for, you got to open it. Well, you could open it like a door, like hinge it toward the water. I don't know how it works. Hinge toward the water, slide it up. I'm not sure how it opens, but somehow it opens. But the point is how hard is the water actually pushing that against the door? So hydrostatic pressure. And let's say that, I don't know, how deep is Lost Creek Lake? Let's make it, I don't know, 112 feet deep to the bottom of the lake.
It's really deep.
Yeah, it's pretty darn deep. I actually don't know if that's an underestimate, but Hoover Dam is probably 300 feet deep. So, there's plenty of dams that are plenty bigger than that. So what we want to know is kind of how much force is against the door. And it turns out this is going to take an integral. Now you might think, why in the world would it take an integral? Well, would you agree that this stripe of the door right here has less pressure on it than a stripe of the door down at the bottom would have? Does that make sense? Because there's just more weight down there. As I said, even I couldn't even breathe 8 feet underwater. I mean, it's amazing how much pressure develops quickly. Well, let's figure out how much weight is on that stripe right there, just that stripe. And since this is vertical, I'll say this is a distance of y off the bottom. So in a sense, I'm going to think of this as the XY axis. So I'm going to put the axis on the ground. And so it's y up. And that would mean that this distance down is 112 minus y, wouldn't it? So in other words, if you're 4 feet up off the ground, then 112 minus 4, that's how deep that little stripe is. Now, so as not to overwhelm you with this and just to make sure you kind of understand it, let's just do a quick kind of a side calculation over here. Let's say this is a foot deep or a foot tall. This is like a stripe, except it's a bigger stripe. And let's say it's 3 feet wide, and we'll say it is, I don't know, 10 feet underwater. And let's just find out how much weight is on that. Well, would you agree there's 10 feet of water on the top of that? And in the end, that stripe, although it's kind of sideways, I don't know if it makes sense to you, because water doesn't compress. If it turns sideways, it still has the same pressure pushing sideways, because water kind of pushes in every direction. And so really what that stripe has on it, since this is 3 square feet times 10 feet, that has 30 cubic feet. I guess I'll write it this way. You have to think of that as having like a column of water, 30 cubic feet. So that's like 3-story. It's like a 3-story building. And it's a 1 foot by 1 foot column of water. And again, imagine it's you. It's like laying on your chest, 1 foot by 3 foot. You have 30 feet of water on you. Well, you might say, how much does that weigh? Well, here's what I had to look up just a second ago. Water weighs, looking this over here in my notes. Where did you go? Water weighs 8.35 pounds per gallon. look that up online, which is kind of helpful, except for our volume measurement here is not in gallons, it's in cubic feet. I also looked up and there is 7.48 gallons in 1 cubic foot. So if I take 30 cubic feet, and ultimately what I'd like is weight. So unit analysis, the ability in a physics or an engineering class or chemistry to get what you want. I want to know how much that water weighs. In other words, I want to know how many pounds of water that is. Well, I've got cubic feet, so that means I'm going to need some expression with cubic feet on the bottom so it will cancel. Hey, look, here's one. And it turns out there is 7.48 gallons. So notice that would get me, cancel, that would get me into gallons. And then I need rid of gallons, therefore I need gallons on the bottom, and I'd like pounds, so I need pounds on the top. Sweet. I go look up online, how many pounds in a gallon of water, or how many gallons in a pound or whatever. I get 8.35 pounds in 1 gallon. So now I know what math to do. I take my 30 times 7 times 8. Whoa, that's like 56. You got to be kidding me. 30 times 7.48 times 8.35. Whoa, whoa. That is, my friends, 10 feet in the water. You've probably swam down 10 feet. That is 1,874 pounds. Wow, like dead. I'm dead. That is a lot of pressure. And that's only 10 feet down. How far is our door down? 112 feet. Oh my gosh, there is a lot of force on this door. You can't just kind of put a door there and then fill this lake up with water. One of two things is going to happen if you don't think this through. Either the door is just going to blow out and all the water is going to go, or the door is strong enough, but then when you try to open it, can't do it. Like there's so much pressure and friction that you can't even move the door. And then the water fills up in the lake, goes over the dam breaks, everybody dies. Like someone's got to think this stuff through. So let's do our problem now. What I want to illustrate is, does it make sense if I went down another foot, not 10 feet, but I went 11 feet, then that's even going to be more weight? Well, do you see our problem over here with our little stripe? So that stripe is at a certain depth right now, but then this stripe down here is going to have more weight, and this stripe down here is going to have more weight. Well, I'm going to have to add all of those up. Every little skinny stripe has its own weight on it. And so I need to add those all together. Like this is what integrals do. They add lots of little things together. Let's see if we can do what we just did with this stripe that actually moves up and down across the door. So we know that this distance is 6 feet. What am I going to call this height right here? You should know the answer to this from everything we've been studying. How tall is that little stripe?
dy.
dy, a little bit of y. And so isn't the area of that stripe, just like over here, we got 30, well, we had 3 square feet. Isn't the area of that 6 times dy? So that's the area. And then didn't we multiply by the depth? How deep in the water is that stripe?
-12 minus y.
Yeah.
Or 112 minus y.
That's exactly right. 112 minus y. Now I won't bother to write this in, but that's 6 feet. dy is feet, and 12 minus y is feet. So do you agree that's still cubic feet? It's exactly the same calculation I made over here. So that's cubic feet, which I then needed to multiply by, I'm going to multiply this out, 7.48 and 8.35. I'm just going to multiply that and get one number out of it. 7.48 times 8.35. I get 62 point, I'm just going to round it off, 62.46. Again, you're not going to have an assignment on this. I'm not going to put it on a test. So ask me questions. Like, I want you to get this. This is just cool. This is the kind of stuff you can do with calculus. And so what that does is well, that's exactly what we just did a second ago when we got this number of pounds. But that's just that location. Would you agree that I now need to come back and add all of those weights up while y goes from what to what? What values does y take? Notice I called,
From 106 to 112.
yeah, notice it's not, it sort of depends what I call y.
8 and 0.
Now in my case, because I called y this measurement here, in other words, that was the distance off the ground, then it's actually just 0 to 8. But I completely understand it. And heard who said that. Why you would say, because I could have called y this distance here.
So I'm confused on if we're, because it seems like we're, yeah, so you put it right there. So wouldn't it just be y then? Because it's kind of like we're touching the y-axis instead of 112 minus y.
Yeah. So since I said this is going to be my y value right here, then y itself is going to be everything from 0 to 8. So I need to add all of those up. I need to add all of those, well, pounds. Every one of those is its own pound, and I need to add all of those together.
I just think my biggest confusion is because you're adding, because I thought we were rotating around the surface of the water, and that's why we added 112 to give us that like space, and then minus y. But if we're on the x-axis on the sea level, then aren't we just 60y times 62.46?
I'm not totally sure I understand your question, but would you agree the area of this door is 48? And I could do this really similar to this over here. If the area of this door is 48, the only problem is how deep is it? Is it 112 minus 8, which is 104? In other words, the top of the door is 104 feet deep, right? That's 104 feet deep, but the bottom of the door is actually clear down at 112 feet deep. And do you see the problem? It's like, how deep is it? Well, although this is 48, well, what's its depth? Well, you could make it the average. You could say, well, it's roughly, I guess that'd be 4 feet off the bottom, so 108. And that would actually be pretty close. If you took just exactly what we did over here, you said area is 6 times 8, and then you said, how deep is it? Well, it's an average of 108 feet deep. That's going to be pretty close to the right answer. But what we're doing is more accurate if it matters, because we're saying, well, what's our area? Well, each stripe is at its own depth. So what's the area of that stripe? It's 6 times a little bit of y. That's its width and its height. And then how deep is it? Well, its depth, since I called the distance the stripe was off the bottom y, then that means its depth is 112 minus y. So that's the depth right there. Let's add that to the. So basically I took area, I took the area of the stripe times how deep is it times the weight of water. And since everything is y's, then I said, okay, well, what values does y take? Well, based on my drawing, y could be 0. Y would be 0, which puts it at the bottom. Since I called y, how far is the stripe off the bottom? The y could be 0, but y could be 8. That would allow it to move all the way from top to bottom. So let's figure out what that is. To simplify, this is not a hard integral to take. It's just hard to set the dumb thing up. So if I take 62.46 and multiply by 6 just to get all the constants, then, and those can kind of come outside, then that's 374.76. It's sitting outside, and then all there is inside is 112 minus y dy. That's all that's left inside. Well, that's an easy integral to take, you say. The integral of 112 with respect to y is 112y. The integral of y is y squared over 2. Now, if I evaluate that at 8 and 0, and of course 0 is nice because I don't have to even put it in there, and don't forget our 374.76. So if I put 8 in there, 112 times 8 minus 8 squared divided by 2, big number, 864 times my previous number. Ba-bam! Oh my gosh. I got, remember the units of this, and you can follow the units through, are pounds. I got 323,793 approximately pounds. Whoa. Whoa. There is 300,000 pounds of pressure on that door. We're going to have to get really serious about building that door in such a way that it does not just get blown out of the dam. Once we succeed with that, we're going to have to think, how am I going to put bearings on it? How am I going to be able to open this with that much pressure against it? And again, this is not dissimilar from you walking over to a block of concrete weighing 300,000 pounds and saying, okay, lift this thing up. Like a forklift is not going to lift that. I mean, there's even technology. This is not simple. You tracking? So if you find this interesting, rather than the assignment, go investigate this and send it. Send it to me, and I'll actually send it out to everybody else. Like, how in the heck is this done then? How do you have a door at the bottom of a dam that is strong enough not to get blown out and is capable of being opened? How the heck is that done? What's the engineering? Who's figured out a way to make that happen? I mean, this is what engineers do. I'm teaching statics right now, and that's the kind of thing that I'm teaching students. Integrals pop up in this situation. I'll give you one, if you do choose to go Google search this and you find it interesting instead of the assignment, I will give you one hint. One design is called a tainter gate, which is really cool. It's probably some dude named Tainter that invented it. It's probably the reason it's called that. Most things that you hear about of this nature are either named after the person that invented it, or the person that invented it named it, or it's just kind of common sense. Wow, that guy made a cool gate. You know, that was Tainter's gate. Yes, I think I came up with that. So it ends up just being called a tainter gate, and you know, we don't hear it as a name. It sounds like tainted or something, and so you just don't think about that. But God, it's so interesting to just go look historically at, you know, when was this stuff invented and why did they invent it and how big was the first dam and, you know, those kinds of things. It's just weird. This is how calculus shows up in the real world. Someone says, hey, go design a dam. All right, awesome. And then all of a sudden you need calculus. And of course, you know, millions of dollars are spent on this. It's like you got to know it all ahead of time. Does that make sense? Water is just fascinating. If we had more time, I would change that gate to be like a circular gate or some other shape. I made it a rectangle, which made it super simple. But can you appreciate if that bottom gate was round? Now the width of the gate down here is really wide, but then it's really narrow up here. And so the width is not just going to be 6. The width is going to be a function of where are you on that half circle. And so all of a sudden this problem gets kind of much more complicated. Or what if the gate was a triangle at the bottom, so that the top was really short and then the bottom was really wide? And, you know, would you be able to write the equations that would allow you to figure out how the width of that changes? In our case, the width just stayed 6 the whole time. It was super easy. Look at that, 6 every single time. Awesome. Well, that 6 would get replaced with some kind of an equation over here based on the equation of a circle or based on the equation of a line. So it's like I could spend 2 days on this and, you know, make you better at integrals. So, you know, would you be good enough in the real world if you ended up someplace where you were designing something like this? And by the way, wouldn't that be awesome? Can you imagine being the person that designed Hoover Dam and it works? And that's so cool. Let's see. What else do I want to show you? I think I'll show you. I think I'll show you one of the problems that was in the book. That's kind of cool. And that is this. 2. Spring math, springs and how springs work. And you're familiar with a spring in the sense that if you pull on it, it stretches, and it's actually harder and harder. The more you pull on it, the harder and harder it gets. Come on, man. Silence your phone. The harder and harder it gets. And by the way, it's not just springs, it's anything. Like push on a tree branch, the branch is sticking out and you push on it a little bit. And then the harder you push, you have to push harder and harder and harder to get it to go away from where it actually usually is. So this is just true of almost anything. When you're, if it's flexible and you try to push against it, it'll get harder and harder and harder. And so maybe you're familiar with the fact that, and this is one of the applications that's in your book, work in physics is equal to a force times a distance. And that's interesting in the case of a spring or a branch, because unfortunately you can't just push with the same force on the branch. In other words, hey, I'm going to push that branch, I'm going to push it over like 4 feet. Well, you have to push harder and harder and harder. Every single sort of inch you push, you now have to put more and more and more force on it. So the force is constantly changing, just like it was at the bottom of the dam. You go down a little bit, more force because you're underneath more water. You go down a little bit, more force. So in the case of a spring or anything that's flexible, the force is constantly changing. And so how are you supposed to find the total work done to push that thing over, or to lift the dam door up, so to speak? How are you supposed to find out how much work is done when the force is changing every single time? Well, that's what integrals do. So here's an example of kind of something that was in your book, if I remember right. Let's say it took 12 pounds to move the spring. And I'm not thinking like a little teeny spring. Think something like a car spring. The reason you have suspension in your car so that when you hit a pothole, you don't just smack your head on the ceiling. Like those were innovations. Or I'm a mountain biker and I've got shocks on the front of my mountain bike. It's like this is more ubiquitous than just some stupid little spring that you play with in a physics class. It's like, that's cool because it gives you access to that, but we're talking about something a little bit bigger. So what if it took 12 pounds to move the spring, say 8 inches, and I'll say out of place, because it has like a natural length. If you don't touch it, it's just sitting there. But then if you go up to it, you can either compress it or pull on it, whatever one. And it took 12 pounds to basically stretch that thing out 8 inches. Well, it turns out that in the case of springs, the force is proportional to that distance. In other words, if I wanted to double that, if I wanted to double it to 16 inches, then I'd have to double the force, which is kind of a cool discovery, isn't it? That mathematicians made or physicists made. If you want to double the distance you push on that tree, or you bend or you pull that spring out, you actually have to double the amount of force that you apply. That's a cool discovery. And that is called the spring constant. Maybe I'll simplify this a little bit. I used a Greek letter there, but let's just use K for constant. So if you take physics, you'll be told this. Okay, well, based on what I just said, then, if you know the force is 12 pounds and it moved it 8 inches, if I divide that, I get, I guess, 1.5. I get 1.5 pounds per inch. That's a way to discover the spring constant. In other words, the spring that I just stretched on, it's just a piece of metal laying there, or some branch I pushed on. I mean, if you had a scale, like even a bathroom scale, and you went out to a tree branch and you just pushed on it and you measured how far you pushed it, and you looked and it was like, 82 pounds, you could actually establish the spring constant of that tree branch, which is kind of cool to think you can do it that manually, if you will. It's not perfect. It's not a physics lab, but there's the fact that I can actually take those kind of measurements. That's really cool. So now if I ask the question, what would the work required? And the reason work is a thing in physics is because that's like how strong does the motor have to be? I mean, if you're having a motor do this, or in my case, I was riding my mountain bike the other day and I kind of went over this little jump and the front forks completely compressed. Like I felt it go bam, metal on metal, like it bottomed out. And so it's like, ooh, that was too much work. Like too much, the jump was too much work. I got to adjust that. I can fix that in my mountain bike. And so, like either don't jump that anymore or, don't bottom your springs out. So that's what work is really like, what work is really quantifying. What if I wanted to find the work required to move the spring from distance 0 all the way out to, say, I don't know, 14 inches? Do you see why this is an integral problem? Because does it make sense that first inch, you don't have to push that hard? Does that make sense? Like you're not pushing very hard. You don't have to apply much force. So, maybe your force, well, it isn't going to be 12 pounds. Maybe it's only like 1 pound to move it the first inch. But then when you go to the next inch, now you're up to like 3 pounds. And then you go to the next inch and now you're up like 5 pounds. You're constantly having to increase the force. And so the force is changing all the time. So I can't just take, it's not the same force. So I can't just say, oh, it's 30 pounds times 14 inches, 30 times 14, I'm done. The force is constantly changing. Well, this is what integrals are for. It's like, oh yeah, we'll just use an integral then and we can add them all up, even though that thing changes, no problem. So I'll conceptualize this as physics teachers always do, is some stupid block or something. And I'm just going to pull this in such a way that it goes from here over to here, 14 inches away. So I'm effectively calling this kind of the XY axis. In other words, that's 0. And would you agree if I pulled it a little distance away? In other words, if I say pulled it to here, then I could call that a distance of X. And then I'm going to let X go from 0 to 14 and kind of add all of those up. So what would the integral for that look like then? Well, remember, work is a force times the distance. So I'm really adding up a force times a distance. I'm adding all of those up. So what is our distance in this case? Well, what we're doing then is saying, I'm going to add up this force, but my distance will be a tiny bit of X. Does that make sense? Because I can't move it very far before the force suddenly changes. Do you understand that? So I have to move it just a tiny amount, because even if I move it 0.1 inches, the force changes. And so I've got to move a tiny distance. And based on this discovery, that force is really equal to the spring constant times distance. That's the way you'll see it in a physics book. Force is, instead of writing force is proportional to distance, which I think is much clearer up here, you take force divided by distance and you get a constant answer. That's the cool discovery. Then all I have to do is replace my force with, well, K times D. Well, we figured out K, it was 1.5 times our distance D, which in our case is X. And then there's our dx. So this is our force. That's our distance. We're going to move it. And then we say, okay, great. Everything is kind of based on x's now, and I'm going to let x go from 14 to 0. Notice at X is 0, the force is 0. At X is 1, the force is 1.5 pounds. I'm just plugging in. I'm just trying to think this through. When X is 1, 1 times 1.5 is 1.5 pounds. When X is 2, it's 3 pounds. Do you see how the force is changing? So if I just add those up, and then you should look at that and go, oh, wow. I mean, the hard part of this is just conceptualizing the integral, like even figuring out how to write this down. And the taking of the integral is like super easy. So that's a piece of cake. So 1.5 x squared over 2 is the integral. And I just have to stick a 14 in because 0 is going to be 0. So it's 1.5 times 14 squared times 14 squared divided by 2. I got 147. What would the units for that be? Because I was a little footloose and fancy free. Think back to force and distance. What was our unit of force?
Pounds over inches.
It's pounds. So force was just pounds. The 1.5 was pounds over inches, but then I multiplied by x, which is in inches. So collectively the force is in pounds, and then x was in inches. So work is a force times the distance, pounds times inches. So this is pound inches, if you will.
Pinches.
That's right, pinches. On a side note, here's something I've wondered about. Maybe you've all bought those Papa Murphy's pizzas, right? And so, it says like 12 minutes at 375 in the oven, right? So, one option is to just let the oven heat up to 375 and then it goes ding, and then you open the door, throw it in there. Hey Siri, set timer 12 minutes. And then you pull it out and everything's beautiful.
Okay, your timer is set for 12 minutes.
That's totally funny. I hope that means there's a pizza in the oven too. That's hilarious. So in 12 minutes when it goes off and I've forgotten, then I'll try to figure out how to turn that timer off. Hey Siri, what's a tainter gate?
The tainter gate is a type of radial arm floodgate used in dams and canal locks to control water flow. Would you like to hear more?
Hey, yes.
Would I lie to you? No. No, I would not. Please go away. You're interrupting me, Siri. Where was I before I was rudely interrupted?
You were about to revolutionize Papa Murphy's Pizza.
That's right. Thank you. So what I've wondered that I've never bothered to figure out is it seems like a waste of energy and electricity and it also takes more time. But what if I threw the pizza in the same time I started the oven?
You'd be a crazy person.
That's a good idea, except for it's not up to temperature when you first put it in. And so in a sense, it would spend like 1 minute at 50 degrees, and then it would spend the next minute at 80 degrees, and then the next minute at 100 degrees. You see what I'm saying? The end result is if you had, let's say 12 minutes at 375 degrees, if you multiplied 12 times 375, that would be 4,500 degree minutes. Does that make sense? Of work that was done to the pizza. So the question is, could I make an integral up that would allow me to put the pizza in right off the bat and figure out what it would take to get up to 45 degree minutes, 4,500 degree minutes. And then, the end result is rather than waiting, say 8 minutes for it to get up to 375 and then 12 minutes for it to cook. So it took 20 minutes. I would be able to put it in right away and it'd be ready in like 17 minutes and I wouldn't have wasted any electricity. I think that would work. I just have never.
Yeah, but then there's the fact that you're putting the pizza in there when it depends on what type of like element you have heating your oven. Because if it's like an electric element down there, it's going to be red hot and potentially just either drying out your pizza or burning it on the bottom.
True. If it was in convection mode, I think that would fix that. But
am I the only one that actually cooks, like doesn't preheat their oven first?
Do you
No,
just feel it?
I don't
You
think
just-
I've ever preheated an oven. It goes in as soon as the buttons hit.
You guys are all crazy. You have to preheat your oven.
Yeah,
Maybe like 30 seconds.
that's why I usually use an,
Hey Siri, is it better to preheat your oven to make pizza? Let's find out.
Okay, I found this on the web for is it better to preheat your oven to make pizza? Check it out.
Can
It
you
is most certainly better to
pizza in
preheat.
the oven before it's preheated? Actually, it might work out just fine. I don't know. It's up to us to answer the question clearly.
Let's settle this thing.
Of all the experiments you could run, one that involves eating pizza seems like a pretty good one to me. Next time, I'm going to commit. Next time I make pizza at home, I'm going to do this. I'm going to make the integral. I'm going to try to figure out how that integral works, and I'm going to cook it, and I'm just going to see how did it work.
So
No, it'd be really good would be to have two pizzas and put one in at the start and then throw the other one in, when it got to full heat, and then like, which one's better? Or are they not any different at all?
yeah, then you can taste test. Cause being cooked and taste tests are two different things. If you say something's cooked, yeah, it's cooked, but does it taste good?
Here's what else I think. I think at the end of spring term, those of you who stay with me the whole time, and maybe COVID has lifted a little bit, I invite you over to my house where we make 3 pizzas that I buy, and we have a whole bunch of mouths. Like we can't just have one person's opinion. Everybody's mouth is on this. Does that sound like a good plan? That sounds like a good plan to me. Well, all right. We'll think about that.
I'm just thinking, what is like the first obstacle? Because I guess I was thinking that we need to know the maximum amount of work that's done in the preheat time to do the equation. Like I'm kind of curious on how to set it up.
Yeah, well, I haven't thought about this, but I don't remember exactly, but if it's like 12 minutes at 375 degrees, I think I already multiplied this, that would be 4,500, I think, degree minutes of, I guess I'll say work or energy. That's like, and to Justin's point, you can't just say, well, I'll put the pizza in there at 4,500 degrees for 1 minute. That doesn't seem like that would work, does it? It seems like a pizza would just go start on fire. So there's a chance that won't work, but it would put the same energy into the pizza. The question is, is it better for it to be low and slow? And, can you cut it in half and set the temperature to 200 degrees and then leave it in there for, 25 minutes? So, that's a complicated problem, but the point is, that would be the formulation of the integral. If this does work, it would be putting 4,500 degree minutes of work into it. But again, the beautiful part about this is the temperature is increasing all the time, just like the force in the spring was increasing all the time. When you leave this class, if you can get book problems right, I don't care, because no one's ever going to ask you any of these book problems. What I care about is if you run across a place like this, somewhat humorous example I'm making up, where something is changing all the time, the temperature is changing all the time. Can you conceptualize that as an integral and actually, like, this is what integrals really are. This is why people invented them in the first place. They did not just think, I wonder what the integral of sine of e to the x is. Like, nobody cares. It's something practical, Of course, it'd be good to be both. So anyway, there's another extra credit. Report back.
I just thought of another variable too, because generally the thick Chicago pizzas are cooked at longer times at 375, whereas the thinner ones are cooked at a higher temperature, but at lower times.
That's exactly right. And of course, if it's thick, you got to get the heat to go all the way through it, but you want to do that in such a way it doesn't burn the outside, right? And so there's more to this than just putting the amount of energy kind of into the pizza. And so that's, but again, shouldn't we experiment with this? Seems like it.
Justin, I like where your head's at. I'll meet you up later. We'll get this done.
It does need to be done. So last application, because I think this is going to take us to the end of class, and this is something I do every day nearly. Torque is a force times a distance as well. And what that is, though, is not work. Notice it's the same exact equation, isn't it? Force times distance, that's work. But torque is like taking a nut and putting a wrench on it. Oh, Lord, do I dare try to draw a wrench? They're going to know that you're an idiot when it comes to drawing. Cheyenne, can you take over and draw a wrench for us? Dr. Seuss needs a wrench too. Like, it can't always be a good wrench. So if you want that nut to turn, you sort of have two things you can control. You can just be muscular and strong and have a really strong force, or you can increase that distance right there. So if you're not strong enough, then get a longer wrench. Is that familiar to you, just as a human being living in the world?
Oh yeah.
So anybody change the tire? It's like, oh man, I can't get this nut to crack. So you got to jump up and down on it or something stupid like that to try to increase the force. So torque is a measurement of sort of, I don't know, I guess I'll say rotational power. I'm not using that in the strictly physics sense for those of you physics people. But the point is because that's a multiplication, you get to multiply those two things together. Well, of course, what's interesting is, what if you have a whole bunch of those to add together? Now, why would you have to do that? Well, let me show you why right now. So here's what I do in construction constantly. I've got this wall, this couple of walls here, and I want to put a beam on top of it, which is what you do every time there's a window in your house, because glass can't hold up the roof, or every time there's a door. And this is what you do on a bridge. Anytime I got water that I want to go underneath it, this is a staple. This is the most basic concept in all of engineering, is a post and beam. I got two posts, and now that beam is going to carry the weight that's above it. The cars that are driving across it, the trains that are driving across it, the weight of the roof. And as long as the beam is strong enough. But do you agree that this beam wants to break under load? In other words, it sort of wants to crack right there. And there's a force here, and a force here, and a force here, and all the way down this beam. And every one of them is at its own distance. Does that make sense? So it's like distance 1, distance 2, call that force 1, force 2, force 3. In the case of like a bridge or the roof of your house, does it make sense it's putting force everywhere? And when you design a house, you have to design it as though it's sort of full of people. In other words, it's got a certain amount of weight, but it could be that people are everywhere. It isn't just one force and one distance. It's a whole bunch of forces and a whole bunch of distances added together, that would equal the, if you will, desire to break. Does it make sense? The beam has to resist that, whatever the structure internally in the beam. And by the way, that can just be you cut a tree down and you're done. There's the beam. But it could be in the modern world that you glue layers together of, hey, there's the alarm, off, turn off. Hey Siri, turn off the alarm. What do I say? The button, that's what I say. Do you see the formulation of an integral here? Lots of forces, lots of distances. And that creates what engineers call moment. I'm only introducing that word because I'm going to show you something official in a second. Moment and torque are virtually the same thing. So engineers calculate moment on a beam. And you can appreciate, if you found out sort of how much moment or torque or desire that beam had to rotate, then you better go pick a beam that can handle that, right? So watch this. fail. Let's see, download. Where am I? What am I doing here?
Have you heard of the floating dance floor at the Crystal Ballroom in Portland?
I have not. Please explain. Wow.
So,
Remember.
so it's like a second story dance floor made from like, it was made like a long time ago, like earlier 1900s, but it's made from beams of wood that are kind of like woven together. So like when you're out there and there's people dancing on it, you can feel like the whole like floor is moving around and like juking with the music. It's really neat.
That's totally cool.
But I'm just wondering, it's like, did they use something similar to this, like to figure out how they can hold that many people on a floating beam floor, you know, and still have it not break?
Yeah, that's the essence of what engineers do. So
Given that it was the 1900s, I wonder if they used math for that or if they didn't use math and ended up with that.
there's a lot to be said for trial and error. I mean, unless, you know, millions of dollars are involved, or, you know, hundreds of people's lives, a little bit of trial and error, having one guinea pig to like test it out is, you know, that's not terrible.
I was thinking it might have been an accident that it floated, but
Well, it turns out
No, it was designed like that.
almost all engineering was invented by people that studied failures. And so it's like, well, why did that fail? And then they, you know, sort of figure out the math as to, and obviously you're trying to avoid that because people die and so forth. This is page 31 out of a downloadable document about beam strength. And what I want you to notice here is off to the side, it tells you, just look at this to keep it simple. See how that's a 3.5 inch wide by 14 inch beam right there? So it's 3.5 inches wide by 14 inches tall. And what I want you to notice is this number right here. See how that says allowable moment? Notice the measurement. What's the unit for that? Foot-pounds. Force in pounds times the distance in feet. That beam will allow, apparently, 29,000 foot-pounds of, and again, notice it's kind of like half. This half of the beam wants to rotate downwards because of all those forces and distances. It'll allow 29,000 foot-pounds before it goes and everything breaks. Isn't that cool? Like, that's been tested to design to do that. So let's figure out where that calculation comes from. Let's do that for a real beam. Ready? Ready, begin. So here's a piece of software that I use called BC Calc, Boise Cascade Calculator. What math do I have to do to use this? Virtually none, as I've been telling you, because this is hard and it's important and you can't afford to screw it up. So I'm speccing exactly the beam here that I just pointed out to you. It's a 3.5 inch wide by 14 inch tall beam. Now in my case, what's really cool about this is, see these percentages right here? All of those are less than 100. So it passed. I'm doing nothing. Like, I'm just typing in the basic constraints, like how long is the beam and how much of the floor load or roof load is on it. And then if any of those are more than 100, they turn red. You know, it's like, burn, you failed. And then I just go in and choose a larger beam until they turn black. Like, it's pretty automated, but calculus is built into this. That's what I want to show you. That's so cool. Notice that very top one there. Moment. The very top thing, something fails. And notice in this case, it's kind of a toss up between how much is the beam going to deflect or bend down and its moment. And so you can tell, because those are both 96, 94%, I chose a beam that's pretty close to failing. Like, you can't spend people's money and, you know, put a giant beam in there. It's like, it'll do the job. Awesome. Well, let's try it. Let's figure this out. I'll draw a picture of this in a minute, but I just want to expose you to the real world a little bit. So this is a roof beam, which means it's holding up roof load on a house. And this is the important thing to know about roof load. Looking right here at the standard load, it says in pounds per square foot, there's 15 pounds of dead load and 25 pounds of snow load. Snow load comes and goes. That's why it's called snow load or live load. Dead load is like the roofing itself, like tar paper, shingles, that kind of stuff. So together, that's 40 pounds per square foot. So that's how much roof weighs. The second thing that's noted over here, and I don't have to type that in, I'm not making those decisions. This is the decision I'm making, which is how much of the roof is actually on it. Does it make sense? You could have a little tiny section of the roof that's sitting on this beam, or you could have a huge section. I have 23 feet. That doesn't tell you that that's feet there. I have 23 feet. I wrote cubic feet, that was square feet. I have 23 feet of roof that weighs 40 pounds per square foot sitting on this beam. Does that make sense? And then the other thing is back here, self-weight. Notice this beam has 13. What's its unit? Pounds per foot. So the beam itself weighs 13 pounds for every foot of the beam. That's how much it weighs. Well, that adds to the weight, right? So you got to include that. If I choose a bigger beam, then it's going to weigh more too. You got to include the beam itself. And notice from the inside of the wall to the inside of the wall, that's 16 feet 4 inches. And just to keep it simple, we'll say the wall is 4 inches wide on either side. So we're going to just treat this as like a 17-foot beam, just so that I can give you guys round numbers. Okay, we have everything we need. Let's go back to today's notes. So our beam is 17 feet long, and it's sitting on a couple of walls. And we said that it was 40 pounds. So I'll write it the way it's usually written in engineering. 40 pounds per square foot. And how many, and what you have to see is the tributary is times 23 feet. Because every foot weighs 40 pounds, and we have 23 of those. If I take 40 times 23, I get 920. Notice I'm taking 40 pounds per square foot times 23 feet. So what are the units of that 920?
Foot pounds.
Yeah, pounds times feet, or pounds divided by feet, not foot pounds. It's one of these cancels with one of these. It's pounds per foot, not foot pounds. So that means that beam has 920 pounds here, and then a foot later, 920 pounds again, right? 920 pounds again the next foot. So let's figure this out. Let's figure out the moment that's on this beam. Again, what we're really talking about here is this thing wanting to split right in the middle. So we have 920 plus the, what was the 13? Wasn't it 13? 13 pounds per foot of the beam weight. So that's a total of 933 pounds per foot.
Is the 40 pounds per foot the load that we're putting on it?
Yeah, that's roof load. That's the standard roof load. And by the way, that's because this is the valley floor. I'm drawing a house plan right now that's up by Mount Ashland, and it's 70 pounds a square foot because there's way more snow up there. Like, you can't get this wrong. This is a really important calculation. So what do we need? We need a force times the distance. Let's speed this up a little bit. So our force here is 913 pounds per foot. But do you notice that actually isn't a force? A force is pounds, right? So that's not really a force. So what we've got to do then is take a little stripe of this, and I'm going to say that that stripe is a distance of X away from here. Therefore, its thickness would be a little bit of X. So if you take 913 pounds per foot times a little bit of X, which is also feet, because X is in feet, does it make sense you're actually getting 913 pounds? Now we have a force. Just like the water, it was like it's dependent on the area. Does that make sense?
I have a question. I got a little lost.
Fire away.
Where did you get the 913 from?
Because I took the 40 pounds per square foot that roofs weigh, and on my house design, which I didn't show you the design of the house and all that, 23 feet of roof was actually resting on this beam. So it's kind of like this. If this beam was here sideways, and then you had the roof that looked like this, it's like that distance right there is 23 feet. So there's 23 feet of roof that are all kind of sitting on top of that beam right there. And since every one of those feet weighs 40 pounds per square foot, 40 times 23 was 920. Oh, I totally screwed this up. Why don't you guys correct me? I just wrote it down wrong. It's 933. And then I added the 13 pounds per foot of the beam weight, and I got 933 pounds. That's probably what you were asking, right?
Yeah, I saw it change from 933 to 913.
Yeah, and you assumed, as always, that, well, he knows what he's doing. No, he doesn't. I don't even know how to cook pizza. So notice the units, that actually is our force. Force is pounds, and it's now pounds. Its distance is X. So it's 933, but the interesting thing is it's not just 933 every foot. And that would be a decent estimate. So you'd have 933 times, well, half of 17 is like, 9 feet, and then 933 times 7 feet, and 933 times 6 feet. But we're going to do better than that because really I can't go an entire foot. Like the distance changes constantly. I mean, if you move 1 inch, that's now a different distance, right? So integrals allow us to get this answer exactly right. So let's see if we can set up an integral. So force times distance. Well, what's my force? My force is 933. Why am I so fixated on that? 933 dx. That's my force in pounds. Times x, which is my distance in feet. Force times the distance, that's torque or moment. Now I need to add all that up while x goes from what to what?
0 to 17.
Yeah, now kind of is the answer to that. X actually only goes to the middle. In other words, we think of the left-hand side as braking and rotating down, and the right-hand side is also braking and rotating down. And so in this case, we're actually only going from the middle over, which is half of 17, which is, what is that, 8.5? That's an easy integral to take. But again, it's hard to conceptualize, right? Now, again, none of you, very unlikely you'll go design beams. I'm not expecting you just to like totally understand this. I just want you to see that here's all these applications I just showed you where things are changing. The torque is changing because every time you move 1 inch, the distance is different, right? So therefore I've got thousands of weights times thousands of distances. Now the weight isn't changing, it's always 933. But the distance it is away is changing.
So Doug, out of curiosity, if we did 0 to 17, would we see the weight or the force kind of even out on the ends? And then once you get to the center, like 8.5, you'd see higher forces? Or I guess torque, I should say, higher torque.
Well, in the end, what you're really doing is imagining like a beam that was just hanging out in midair like this. Like, let's pretend there was no other side to it, and you just wanted it to cantilever out so that people
The 17
stand out here and look over the edge. And so it's like the desire this thing has to go, you know, like that. If this is there's one of these at the Grand Canyon. There's like a place that people can walk out, and that's actually a glass floor so they can see down. So you got this, you know, heavy deck that wants to rotate all by itself, but then you stack a whole bunch of people on it. And so this thing really wants to rotate down badly. Well, that's what moment is how much desire does something have to rotate? In the case of a beam, if it's supported on both sides, it's not going to rotate like this. It's going to break in the middle, and one half of it will rotate down this way. The other half will rotate down that way. That's why we're looking at it. And so the question is, how much can the beam resist the desire the beam has to bust in the middle and rotate down? And that's what that sheet was telling us about allowable moment.
Okay, I got you.
So this is not a hard integral to take. Let's just get it done. So that's 933 from 8.5 to 0. There's an x left behind and a dx. And so, that's an easy integral. X squared over 2 evaluated at 8.5 and at 0. And don't forget to multiply 933. So 8.5 squared, easy integral to take, divided by 2 times 933. I got 33,705 approximately. And again, the units of that would be pound feet or foot pounds of moment or torque. I won't write it down, but desire to rotate. That's how badly one half of this beam wants to rotate down. So, you know, can we stick a beam in there that can handle that?
Got a question.
Go ahead.
Can you use a subpar beam and then just stick a support in the center there to
Right.
give it more support?
If you put a stick in the center, then now the beam is not 17 feet anymore. It's only 8.5. So that's exactly right. So I either
Still gotta do the math,
choose a
though.
larger beam, or I say, sorry, you're going to have a post in the middle of your garage because there's not a beam big enough to handle this. Somebody else?
Yeah, then you're just doing the math for a smaller beam, but it's not like you can avoid doing the math.
That's right. Yeah, you just end up doing it for a smaller beam. Now it'd be from 0 to half of 8.5, which would be 4.75. It'd be from 0 to 4.75, and you'd get a much smaller number, and then you could choose a much smaller beam. So notice that fails. Do you agree with that? What can that beam support? 29,000 pounds. What did we get? 33. What's the deal? Why didn't that work? Or, you know, I showed you the sheet. Like I said, I chose a 3.5 by 14. Why didn't it work? Or how come it worked? Well, remember, this wasn't actually spanning 17 feet. It was actually spanning 16'4". So it's a slightly smaller length. Like I just rounded things off to make it kind of simple. To make it a little simpler. But you see what I mean? Like that's a legit calculation. Like how many people understand this? And by the way, when I sort of discovered this, and was trying to figure all this out for myself, I called some engineer friends, people that actually know, that get paid to know engineering, and they didn't understand this. They didn't create this. There's formulas for this. What do they do to calculate moment? Well, there's an algebra formula. Like you can make a formula that keeps you from having to do calculus every single time you do this, which of course makes total sense. Like let's not do calculus every single time. Let's figure out how to do it once and for all. If I had time, I'd show you that too. So there's an algebra formula. So I asked them about the algebra formula. I said, well, you know, where did that come from? And, you know, they have no idea. Like they don't know. Because they don't need to. Does that make sense? Like, I don't know, who cares where the formula came from? It works and the building didn't fall down and I made $100,000 last year. So yeah, knock yourself out. No problem with that. But I just think it's fun to understand. And I think what I showed you today is a, you know, kind of a good smattering of 1/10 of the cool places in life where adding up lots of little things where something changes is kind of a cool problem. So notice the machine got 31,000 foot-pounds, which is close to what we got. We didn't get the same thing because I messed with the distances a little bit and so forth, but we're in that ballpark. Like without rounding, we're in that ballpark. It's kind of cool. The first time I ever drew a house plan, my own house, they said, oh, I'm sorry, you got to turn in beam calculations. And I was like, well, I don't know what you're talking about. So I started figuring this stuff out, and I kind of did what we just did a minute ago. I said, okay, cool. You know, and I turned that in to the city, and they're like, I don't even understand that. I don't even know what you're talking about. And so they didn't want beam calculations. They wanted a piece of paper. They wanted a piece of paper with no red on it right here. Does that make sense? Like, people don't know this. This is hard. Like, you got to take a lot of school to actually know something like this deeply. And so, you know, those people down there that are approving plans, they wanted a piece of software that said fine, or they want an engineer's stamp, some nerd that actually knows all this stuff that stamps it and says, I declare this is fine and I have insurance to cover me if it's not. Because not many people can, you know, make calculations like this. And you can see why. The stuff I've showed you today, you're probably glad I'm not creating a project out of this, right? Or giving you an assignment, because it's like, well, I kind of see what you're saying, but it's our first time at this. So, you know, applying it like this seems pretty hard, if you will. And so all I'm really doing is opening a door for you here to look in and saying, wow, this is a really powerful concept that we've been talking about. And so if you end up someplace in life where you need maybe one of these applications, you know, first of all, good for you, because you're going to be building something really cool as a result of that. But you'll figure it out when you get there. Like, it's only one, right? You don't have to know all of them. You don't have to know everything I showed you today. So to me, this is a great time to, like, let's not have an assignment. Just show us this stuff. Show us the door. Hey, that's really cool. Later on, I can go walk in there. You're more than welcome to ask me any questions outside of class. You'll probably ask me questions I don't know the answer to, because most of the things I've learned about this, I've kind of taught myself. I'm sort of a slow learner, and so I understand the things that I've waded into pretty well, but you could very easily ask me questions I wouldn't know the answer to. I'm growing in my understanding of what an integral is and what it can do, like every year, you know, measurably growing every year. I'm better at it now than I was last time I taught calculus, and I've taught calculus, you know, 20 times to people. So I've done it a lot. All right, is your brain full? Empty? Noodleish? So you have given me a quiz to grade last night, and I am going to grade it over the weekend. I'm going to see you tomorrow for review. I've got a review posted for you already, and we're taking the chapter 6 test Monday. I don't imagine I'm going to put any applications of this type on it, because, you know, if I don't make you practice it on your homework assignment, then that's not really fair. So I'm probably just going to give you questions that aren't applications. So tomorrow we're just going to play around with that, make sure you're good and ready to rip on Monday. So, all right. I got you out of here only 2 minutes late today. That's a record. Let it be noted. Stay after if you want to ask me questions as usual, or see you tomorrow.
Hey, I was wondering if I could send you like a picture of my project. I know I'm going wrong. I think it's on my integral.
Mhm.
I
Yeah,
just wanted some feedback on that.
yep, that would be a very good use of our time right now. The project is really cool, and I would love to one-on-one help you diagnose that. So you're going to email it to me or share a screen? What makes more sense?
Just sent it to you with text because I don't have it on the computer here at work.
Okay. Text. And you're doing surface area or volume and you're wanting to check the answer, or tell me?
Yeah, the first one I have on the front page, I have the volume, and I had my volume total as 481.49 centimeters cubed.
That's too much.
Yeah, see, I think I'm getting my integrals wrong because I know my surface area. The second page is my surface area calculations, and that's also wrong. So I'm not really super certain where my issue is. I've done it a couple of times.
Sure. So let's do this. I just forwarded it on to my email so that I can make it a little larger. It's kind of hard to see on my phone anyway. And plus, other people are hanging out. Maybe we'd like to learn from your questions too.
Okay.
If you're okay with that.
I am. And also, how is the presentation?
That's a good question. And I'm not looking for like bells and whistles. I'm just looking like for, can you follow some steps through it, and is your handwriting recognizable as a human being's work? Was there a human at a glance? Awesome. So the first of the 2 pages you sent is
My equation and the volume.
Rotate clockwise. Okay. So talk me through this. Your mind, and I'll sort of follow your logic as I'm reading this for the first time, and then we'll see if we can determine where you went wrong since the answer is not right.
So I solved the equation for y, which I worked on with a couple other people yesterday, and you gave us an okay with the equation. So then for the volume, I did 2 pi x, and then I did the one function that was.
And are you, with respect to volume, are you thinking of this as cylindrical shells, or are you think of it as discs or washers?
I think this was the washer. I used the book to help me set up the formula. Because it says, like, I was trying to go around the y-axis, and I was trying to just use the simpler of the formulas from the book. I can pull up the book on my phone.
Yeah, try to tell me which one, because I'm more concerned because of today's discussion. The only place you'll ever use this is doing something practical. And this problem I'm giving you here is an example of something practical. And so the ability to conceive of what you're doing is so important, because it's so easy to throw these kind of formulas at it because they're so complicated to throw a formula at it and just kind of go, I don't know, is it right? And
yeah, I did the shell method about the y-axis.
That's exactly right. Notice
so it was 2 pi x, and then the top function would have been y equals 4. So that's where I had the 4 from. And then minus the lower function, which would have been the curve.
Yeah, so let's talk about that. So the very fact that it said 2 pi x, I immediately knew that you used shells, and so should have you, because shells is the circumference of the stripe as it sort of flies around times the height times how tall it is. So when I saw 2 pi x, and first of all, I would agree, notice the distance, the radius to your stripe would be a distance of x because it's horizontal, right? So it'd be 2 pi x times how tall is the stripe. Do you agree with that?
Yeah.
Well, that's what's wrong. How tall is this stripe right here? How tall is that?
Why?
Why? That's exactly right.
So I put
Down
in
here, and this,
y is equal to 4. So that's how I got my first function.
yeah, but y is not 4. Like this is literally just the y coordinate of your circle. That's it. So you have 4 minus something in here as though the height is from here down. Does that make sense? If you say
Yeah.
the y of 4 minus the y coordinate of the circle, then you're giving me the height from here down to here. Whereas
Yeah.
you're giving me the height from here to here, which is just y.
So I should remove the 4. And then because it's in dx, I would still be going from 3 to 7.
That's correct, because this part of it is from 3 to 7. Now I like this, you said, hey, I'm going to go get this A. Now, kind of like, like right down here, when I look at your work, it's like, hey, look, A, B, like that's totally clear. Like you labeled it A, you labeled it B. Here's my calculation for A, here's my calculation for B. And in the case of B, notice you just did geometry, good. You don't need calculus to find that.
Okay, so I'll recalculate that one with no 4 in there because that's definitely, I was kind of struggling with that one. And then the surface area on the second page is, I think I'm messing up my integral again, and I've redone it a couple of times, but none of the answers have came out what I think is, that doesn't seem right.
So again, I'll ask you the same thing. Can you conceptualize what this integral is referring to? So you don't have a picture here to look at just because this is your second page of work. But can you describe, like, what does this 2 pi represent? What does that x represent? What is this whole?
But it's the rotation times the arc length.
That's right. The circumference of the rotation times the arc length, because you're thinking of that as like a strip of paper that's wrapped around this shape on the outside.
Right.
Unwrap it, its length is the circumference, which would be 2 times pi times x, because that stripe is horizontal, so its radius would be x, times that arc length. So this arc length, it would be 1 plus the derivative squared, right? Now I'm looking at Lance going, well, that's pretty complicated. Is that really the derivative squared?
I've got quite a few derivatives squared. I haven't taken Calc 1 in I think like 2 years. So I was struggling with that one because it wasn't as simple as our normal ones.
Mm-hmm. Now at a glance, I would say this looks pretty good. In other words, let's see, your equation was like,
it was a negative square root of a polynomial. So I did the I put it instead of having the square root, it was to the 1/2.
That's right.
And then I subtracted 1 from that, which would have given you the negative 1/2. And that I left the negative out in front of that because there was a negative out in front of the square root.
That's right.
And then I times it by the derivative of the internal function.
Which is really good.
And I don't think I got the answer right though.
Can anybody tell what she missed here? If you take the derivative of jump to the 1/2 power, What's missing? There's one small thing missing. You're actually doing a ton of stuff right here.
Well, that's good.
If you have junk to the 1/2 power, what do you do before you take that 1/2 and subtract 1 from it? What do you do with that 1/2?
Multiply the front coefficient by that.
Yeah, doesn't that 1/2 come down front?
Oh, okay. That's so I just
Yeah,
missed
yeah.
that, and the rest should probably work out then.
That's the only thing I see.
So it would just be so the 1/2 would come down. So would it just be a negative 1/2 times the
Yeah,
rest times the rest of the stuff?
yeah. And I haven't checked if you kind of multiplied that all out right, because you originally had 16 minus x minus 7 squared there or something, it's like I haven't kind of double checked that, but yeah, that's the only thing I see missing there. That's really good.
Okay, because I think on the other portions of the surface area of the top, bottom, and cylinder, I think those look correct, but I know my number was a little bit too big.
Yeah, you're right. This 461 is a little too big, but it's not way too big. So if you're lucky, that 1/2 will fix it. And then
Yeah.
I like your labels over here. It's like surface area of the top, surface area of the top, surface area of the bottom. Like you're speaking, that's a human. There's a human writing all this. I can totally tell what you're doing there. It's beautiful.
Okay,
Yeah,
so I
you
will.
get that out of all the surface areas, and there's all the numbers. Like that's beautiful.
All right, so I will fix the yeah, so I just had messed up with a couple of just like numbers there. So I'll fix the 1/2 and I'll fix the 4 and I'll work that out.
You can text me and ask, okay, now is this number right? And
Okay.
at a glance, I don't see anything wrong. As I said, I didn't do this the same way you did, so I didn't multiply 16 minus x minus 7 squared out. I didn't multiply that out.
That's
So
fair.
maybe maybe there's more to that. Also, isn't there a 4? Like, don't you have y equals the square root of stuff, but then there's a +4? I don't see the +4. I'm wondering why.
When I took the derivative, the +4 went
Oh
away.
yeah, that's right. Okay, yeah, I'm okay with that. You're right.
So yeah, that was after I took the derivative and then squared it.
Right on.
No,
You're right.
that's not, the top one is not before squaring.
Yeah. Uh-huh.
That's just the derivative of the equation. And then the second one, the second line down is the one where it's all the derivative was completely squared.
Yeah. Yep. Because this bottom, which is square root, moves to the bottom, but then when you square it, the square root goes away. So that's wonderful. And then the top, you just wrote it squared. I love what I'm seeing there. That's beautiful.
Okay, yeah, it's probably just the one, since I missed the 1/2. Yeah, that I will try that again, and I added an unnecessary 4 in the first page.
Sweet.
Thank you.
Good job. Somebody else.
So I just have a quick question about the volume part. So it doesn't really matter whether you do it with washers or shells. It just matters if you keep track of what you're doing and you're doing it in the proper manner, right?
Yeah, that's right. And that's kind of one of the reasons I gave this project, because I'm not saying do it one way or another. And, if it was really important, like, is one easier than the other? Could you actually do it both ways? If you did it both ways, could you get the same answer? I mean, you have all kinds of things to think about. In this case, you're able to, I gave you permission to kind of email or text me and say, is this right? In which case you could say, okay, good, I'm done. But in the real world, if you were the engineer, it's like, man, I don't know if this is right. There's a lot going on here. I could conceptualize this wrong. I could have punched a button wrong. I could have left something small out like Alicia did. And so, in my case, I'd think, is there 2 ways I could do this and get the same answer? Or can I drop it in water and measure it? I mean, is there something I can do to check my work here that?
Right. Yeah, I was just curious because I checked my answer I'd gotten before we had separated or ended class last night, and told me it was correct. So it just, when she had gone over that, it was a different way. And I'm starting to realize that a lot of the problems we've done, it's like, oh yeah, you can do it a couple different ways, but which way is the easiest? And is that
Yeah.
readily apparent from the beginning if you're not told.
Yeah. Well, in this problem, I didn't tell you whether to rotate it around the y-axis or around the x-axis. That's kind of up to you. The way it's sitting, the way it's just sitting in the figure that I gave you, it looks like it's rotating around y. So I bet most people did it that way, but I didn't tell you where to put the 0, 0 at as far as the x-y axis that helps you define the equation of the circle. There's more than one place to put it. So other questions, fire away.
Okay, so after you guys talking about Alicia's project, I'm now super concerned that my project is completely wrong. And so for my project, I actually used a torus. A torus is like a donut, And if you take a slice out of the donut next to like the spherical shape, you can see that it's kind of the same shape of your figure, I suppose, if you were to like have a hole in the middle. Do you know what I'm talking about?
No, I absolutely know what you're talking about. Yeah.
Yeah, and then I used a very, very basic, what I could figure out about a Jacobian to explain, so I could kind of clean up the derivative, if you know what I'm saying.
I do.
And then I got, and then
you're amazing.
I got a volume of 146.83. Is that right? And I think I might have done it wrong.
That's right.
No, that's right.
And then I got a surface area, and you said 461 was too large, but I got 489.98.
Yeah, that's too large.
But I don't know what I did wrong.
Yeah, well, I'm happy to help you.
I'm on my iPad actually on Zoom, so if I email it to you, could you take a look and see?
If your method for that was, very dissimilar than what we've done in class, which is often the case in the way that you work and think, it might take me too long in this setting to figure that out. But
actually, I think I might see an error. I'm gonna go over it one more time, and if I still can't figure it out, I'll email you and see if I can get it.
Okay.
I also wanted to tell you, yesterday, I turned in so I had 2 downloads of my quiz, and one of them had a mistake in problem number 6. And so I saw that this morning. And if you can, I suppose you don't have to because I did technically turn in the wrong one, but I sent the correct problem 6 to you in your email. And I know it can get lost in email, so I just want to let you know.
Yeah, okay. I'll be grading on that today. So make sure I get that right, and let me know if I don't, but I should be able to handle that. Thanks for letting me know.
We know Eve's probably cheating on this one, but
yeah.
It's fine. You can grade the one in my open math. It's just I forgot to square it. And so it got the wrong answer.
I see your email 8:30 this morning. So
yeah. Anyway.
Yeah, good job. Keep going. Who else?
all right, I had a question about 3B on the quiz, kind of a side question. Yeah, the one where we're supposed to use a calculator. So I had like kind of briefly looked ahead at integration by parts, and I was like, I wonder if this is even possible. Like, what would you have done? Would this be possible before the days of calculators, or is this?
Yeah, that's a great question. Yes, but you have to be amazing at substitution.
Would it also take like a week, or would you just have to be good?
No, it won't take a week. You just have to figure out how to substitute.
Okay.
In the end,
I tried to do
and I'll give you a
substitution, then an integration by parts, and it was like, I mean, I hadn't practiced it at all. I just looked at it. So
yeah, and that's the heartbeat of math. I mean, it's if a person has time in mind, just to try stuff, like that's what makes it fun, and especially if you actually hit on it and figure it out. It's like, God, that is amazing. But the one hint I'll give you, and this is actually what we're going to study after this next test in chapter 8, is anytime you have the square root and underneath the square root is stuff that's squared, does it make sense that has a Pythagorean look to it? In other words, you have the square root of 1 plus, x squared, and it's more complicated than just x. but you have 1 plus x squared. Well, does it make sense that you could draw a right triangle that described that statement, because there's a 1 and an x that you're adding together and squaring? So does it make sense the 1 could be this length and the x could be this length, and then there's a hypotenuse there? And that's what you're getting when you add 1 squared plus x squared and square root them, is you're getting the length of that hypotenuse. And so the substitutions involve facts about right triangles. And so if you let x be sine of theta, or something super weird like that, all of a sudden you can make some progress. And so we'll be talking about that in the next section.
Okay, cool.
So
I probably won't look into it more. I've got a pretty busy week, but
yeah,
I was
absolutely.
like, is that possible? So,
yeah, it actually
cool.
is.
All right.
Awesome question. Good for you. Who else?
Just real quick, something that I keep confusing myself on. So for our project, when you have a shape like that is on the x-axis and rotated around the y-axis, but there's a gap between the y and where the shape begins, that the radius of that shape is just x, right? And we're limiting it, limits of integration are at the two x values where it exists, right?
That's exactly
so it doesn't
right.
matter that there's a gap.
That's right. The fact that you say x goes from, say, 3 to 7, the fact that you didn't go all the way from 7 to 0 creates the hole. So
Okay.
that's
Yeah,
one of the
'cause-
advantages of shells, because if you send it around this way and you say, hey, this thing only exists from 3 to 7, then the hole is automatic.
Right. Yeah, because I guess like I'll spend too much time doing math and then I start to confuse myself on basic stuff, and then I'm wondering, is
Well,
this
that's
really right?
hard. That's why I'm giving you these problems, even though and that's why I didn't give you guys an assignment today, because these problems are really cool, but it's a big ask. It really is, because it hurts your brain. Like, it really makes you think this stuff through. And my concern is just, at the end of all of it, if I can help you one-on-one and say, here's what you went wrong, because you personally put a lot of time and thought into this, anything I would say to you is going to go in really deeply. You're not a person that just looks at it for like 1 minute and goes, I don't know what to do, and gives up. Like, you're trying things and you're thinking and reasoning and you're pounding your head against it and so forth. So, if you get it, then great, good for you. You got it under your own power. That is utterly amazing. But if I have to, get involved and either take points off and, help you understand where you went wrong, whatever the point is whatever I do there, that's going to go into you in a way that doesn't maybe go in the same as somebody that didn't spend as much time. So, I mean, you're killing it, but all I'm saying is this is hard. You're not going to just sit down and knock this kind of stuff out. So you're doing it exactly right.
I'm glad you asked that question, because I was kind of struggling with the same concept too, but that makes total sense, because it was mainly like the first 2 problems on the quiz. And I was looking at it and it was just like, I was making it so complicated. And then it was like, oh, okay, well, since you're doing the integration from this part to this part, then you don't really need to even worry about that other space there. And I was trying to compensate for all 3 spaces on, like from the bottom up and from the left over.
Yeah, that's painful, no question about it. And you're right, that first question on the quiz is very closely related to what you guys are doing on that project, and I wanted them to work together to help you get it. That's why I said, though, for me, I got to draw a picture of it. Like, I have to literally draw the height and the radius and kind of go, oh, the radius is x and the height is, well, that's not y, that's like 9 minus y, and so that's the height of this little stripe I'm sitting around. It's like I got to draw pictures of it. But the cool thing is if I draw pictures, I don't have to look at formulas in books. I mean, I know the geometry formulas, but I can draw pictures of this and figure it out myself and not have to look at a formula in a book when I find myself thinking, I'm not sure if this is even the right formula. I don't understand how it applies, so that's kind of what I want, some of that for you guys without killing you.
Yeah, I was gonna say 6.6 on the quiz. I think it was the first problem with that weird cone. I think I just ended up recreating the shell method from scratch because I was, over complicating it. So I was thinking, well, I need a pi times the radius for this. Oh, well, I should multiply that by 2 because I've got 2 radiuses. So I need the whole circumference slash length of the shell. And then I can use arc length for the width. Oh, that's the shell method. And there's the arc length.
Yeah. I mean, you won't get it all in your first pass, but to have things dawn on you like, oh my God, that makes sense. To have a few of those high point moments that's enough for one pass,
Yeah, also, for those last 2 problems, I wasn't sure on my answers at first. So I kind of compared them to their less extreme counterparts, like just the surface area of a regular cone without a bottom and the surface area of part of a sphere. And
Yeah.
I wondered if that was a valid.
Absolutely valid. Yeah. Yeah. And that's kind of what I meant earlier. Like if you're the engineer and there's not somebody like me checking your work for you, the ability to kind of go, okay, does this answer make sense? And your first thought should be, I have no idea. What could I do? So comparing it to a cone and saying in that 5A, for instance, the cone curves in. So you'd think, okay, well, that's got a curve to it. So the surface area would be bigger than if it had just been a cone. And so, oh, cool, let's find the surface area of a cone. And then let's see if our answer is a little bigger. And then it'd be an indication that it's like, oh, cool, and maybe I got that right, or maybe not. So I'm punching that in right now. So it's according to the graph, it's a height of 4 and a radius of 2. So the surface area of a cone is pi times radius, which was 2, times the square root of the radius squared plus the height squared. Two, 4. I got 28 for that, which actually is a little concerning because the answer to that question was 21. So I would have thought it would have been a little smaller, not bigger. So now I'm kind of going, what's going on there?
Well, I got 28 for the regular cone as well. And I kind of thought that was okay because a regular cone is going to have a straight side versus the weird one on the quiz. It's got a curved side. So I thought it would have less area.
Yeah, since it curves in, I would think less.
Oh yeah, I think you're right. My initial thought was that it'd be more, but I think you're right. It's actually shrunk in, so it's not going to be as big as it would have been if it was out. So yeah, I misconstrued that. I was thinking about that wrong.
Arc length is more, but the radius is less.
Nice job. That's right. Thanks for linking that Grand Canyon overhang, Logan. That's really cool, isn't it?
That thing is so wild.
That is super legit.
Yeah.
I'm going to click on it. I've seen pictures of it before, but I'm going to click on your link right now. I'll share it for everybody else. Yeah, isn't that crazy? Actually, it's interesting that you found that picture because I didn't realize. I thought it was like a big, like an open walkway, but it's actually like a trail. I didn't, which actually kind of makes sense because it's like, walk this way and then come back in. I thought it had a glass floor in it, but it's actually just.
Yeah, I actually thought it did too. I wonder if there's another something kind of like that somewhere.
I doubt it.
I think it does have a glass floor. It's just the reflection we're seeing from the sky on it. You can't really.
Oh yeah.
Yeah, but it clearly has guardrails, so guardrails on both sides. Like you're not going to walk out here. So they could have a plexiglass floor out there, but they're not letting you walk there. So it looks to me like they have these giant walls to make sure nobody can fall, so obviously someone's going to die if you don't put a tall enough guardrail and blame the government or whatever.
I like how the walls are curved in too, so you can't lean out.
That's right.
My brother was telling me we went to Horseshoe Bend, and he's kind of scared of heights. He was saying that more people die at Horseshoe Bend than at any other place, any other national park. And I was like, really? Like Denali, where they're climbing that? And because people do handstands for Instagram, and so I was out there taking a picture, and he was like holding on to the tail of my shirt, like, get back.
It's for Instagram. Well, the only picture I've ever seen of this was the side view, because that's kind of like the engineering view, looking at the side, because it's, you know, sticking way out. So I guess maybe I just assumed that it was open. Fascinating. Isn't it amazing that somebody could actually design that? And again, it's one of those things you're going to spend $1 million building that, so you can't build it and then you're like, oops.
Yeah.
Are you saying, Doug, that you thought that you were thinking that it was like just a large like open area, not like
Yeah.
a trail that went out?
Yeah.
Okay.
Big dance floor, and then you stood and looked straight down with your legs, and you could see down below, and people just walked around.
Oh.
It looks like there is some glass. Here's yeah, the reflection, just the little center stripe that's like pink is glass.
No, I think that's just the structure underneath it. I think that's going straight down perpendicular to the floor. Here's the floor, and then it turns 90 degrees and goes down.
Yeah. He's talking about like right in the middle of the pathway. That's glass that you can see through, and
I see what you mean right here.
that orange you're seeing, I think, is just the other side of the support on the outside.
Structure.
Oh yeah, that line. Yeah, I see what you mean. So that path actually is see-through. That could be.
You should click on that other picture he shared.
Yeah, I got another.
Oh wow, that's definitely a different picture. Ha, they're laying down on it. You are certainly correct.
This one's actually, all right, one more picture, because this one makes it look just even more extreme. Wait, is this fake? I might have got a fake picture. It looks very different.
Did you send the third one?
Yeah, I sent the third one. They're coming in.
That third one looks like a painting almost.
Yeah, I don't know if that's real, but the side profile is kind of crazy.
I'm still only seeing 2 in the chat.
No. Yeah, it's okay. I think the third one's a painting. So.
Crazy. I think that would take your breath away.
Yep.
Yeah, if climbing Mount McLaughlin gave me slight vertigo, that definitely would. Okay, you guys have a good day.
All right.
See ya.
See you tomorrow.
All right. See you guys.
Bye-bye.